So I'm going to talk to you about the phase diagram of liquid mixtures, and this is what is called the vapor pressure diagram. Okay. So this vapor pressure diagram is because it's a mixtures. We are talking about mole fraction versus, which is the composition, A, versus pressure. So this is how the mole fraction is always 0 to 1, and then we are recording the pressures of component A, component B, total pressure, and also something that we want to deal with. So this is actually, I want you to understand this, and then this is we are going to focus on to ideal gas solution. Not ideal gas, ideal solution. Ideal solution. The later in the chapter, I think it's F or something, they use something called activity instead of mole fraction to describe the solution chemical potential. And this one is to make our life easy, something that's tangible. This is a tangible. I know how to calculate those. And this is something that I know how to control it. So here's a situation, which is can be shown up this far. I've drawn this diagram before, and this is your A, and that's the B. So there are A and B's are everywhere. Right? So this is a liquid, and there is a gas. Okay, so this is a mixtures. So what's important for me is I want to define the mole fraction or composition in the liquid phase. What symbol have I used before? Mole fraction of A? You remember? Yeah, that's right. I've been using this. All right. And also I've been using B, which is 1 minus XA, right? So now, today, I am going to show you, I need a mole fraction in the gas phase or vapor phase, right? And you guys been, in your general chemistry, you use the same XA, right? Remember? You used to say partial pressure is XAP. That's the one that you've been using it. Not anymore, because I use that already. Okay, so in this chapter and so on, because we are dealing with gas and the liquid for different composition, so what I'm going to do is I cannot use an XA. This is for the liquid. I want to be this way. So although I learned this now, I'm just going to not use an XA, but what is your choice? Instead of X. 1 minus X, 1 minus X is the XP. I'm just saying the composition of A, and their textbook count choice is Y. Okay? So this is a YB. This is all mole fraction, same thing. Same thing as your mole fraction. The only difference is this is in the vapor. Okay, so that's they use two different symbols now. And this is what we typically want to do. If you mix the liquid A, liquid B, if you control this composition X, and I want to know how much things are shooted into the air. This is a vapor, and then what's a vapor composition? What's the relationship between these two? Okay, so that's a relationship that I want to know. And you actually learn everything. Just you haven't seen me or anyone using the mole fraction in terms of Y. Just keep track of X and Y as different. Okay, so liquid, I just told you that ideal solution. let's just concentrate on A. So the partial pressure of A is an XA PA star. That's a Raoult's law. Allow me to actually predict partial pressure A from the pure vapor pressure PA star and the liquid property. So this is once again relating the gas property with the liquid properties, right? And the second one, this is even more useful. You remember the partial pressure versus P total pressure, right? So that what you remember the partial pressure, and this is the total pressure. What is your mole fraction in the gas phase? This time you're going to use that, right? So this is a P is essentially external pressure or the pressure that you are measuring. You just break it into the partial pressure contributions. So this equation seemingly fairly simple, right? So all I need to do is combine these two. So what I'm going to do is I want to know pressure, which is total pressure is combination of two gas phases, and then each one is coming from XA PA star, XB PB star. So that's using the same thing, but now I want to describe this one into a 1 minus XA, so that only one variable is being used. So this one becomes now PB star plus PA star minus PB star minus XA. Okay, so a lot of symbols here, right? But what I'm saying here is y equal 1 plus 2x. Do you see that? I mean, I'm just throwing numbers here. This is just a number, right? Your y-intercept, that's your slope, that's your x, and that's your y. Right? So this is your y, quote unquote, in your graph. This is your x, that's your slope. Okay, so what am I drawing here now? This is a diagram that I now wanted to draw. 0, 1, XA, and here I am going to write pressure, which is total pressure, and then you start from the PV star, which is a pure B is vapor pressure from pure B. And then your slope here is on the other side. And what's your pressure and you have a pure A, you can think about this should be PA star. And yes, they are, because the slope here is supposed to be delta X times delta Y. And delta X is 1, delta Y is, this is what they tell me. Okay? So that's the differences. So this is I have the equation for the total pressure, which is, I mean, we've been talking about this before, but now I do have an equation for that. And now, I want to know the relationship between XA versus YA. Right? This is a composition in the vapor phase. If you remember the figure that I just drawn here, this is a liquid. You have let's say 50% of A. Do I have more A or less A? This is something that I want to figure it out, right? So the composition in the gas phase and the liquid phase is not the same. And if this is let's say, I mean, think about it. If I have waters and ethanol in the vapor phase, which one do you think is more there? Should be ethanol rich, because this has a higher vapor pressure than this one. This one has a lower boiling point than this one. Right? So there's more tendency for this one to shoot up than, let's say, just a 1A. Right? So that's a difference. So this equation, which is YA, which is what I want to know, and told you before, this is a P over PA. And so that's the equation, and I have an equation from 3, right? From my derivation from the bottom here, I can just put that in. PB star, PA star, minus PB star, XA. Okay, and the PA star is also PA star. Say. So I can put this one in. All of a sudden that liquid composition with bunch of parameters that I learned from the pure solid vapor pressures, I can predict this one to YA. Right? Can you see this equation? Okay. Don't be kind of tricked by this, all the symbols, right? The whole thing matters is I have a control on the solvent composition, solution liquid composition. This is a vapor composition, is their relationship between these two. Okay. And then now I want to show you this. This is an XA. This is a, let me draw it here. Okay. This is important, so I wanted to, yeah, this is fine. The conceptual, this is an equation, and so now I have an equation for YA. So I want to draw this one versus XA. Okay. And then let's say there's a one case where you are going to have the line looks like this. When do you think that you're going to have a line looks like that? YA and XA is the same, right? This is a Y equal X line, right? 0 to 1. When you have a vapor pressure of pure A is same as vapor pressure of pure B, which is very unlikely, but let's suppose there's a situation just looks like that. You will have a chemical composition in the liquid phase, and this one has a. So what that means is trying to imply to you is when you have a same boiling point, you distill something into the gas phase, the composition doesn't shift. So you don't purify anything. Just same thing goes in and out. And if you look at that, okay, same vapor pressure, so this one is 0, right? So that goes away. And this divided by that is the same, so it's a 1. So YA is XA. So that's the equation that you can come, or you can just simply make sense. This one is the case. Okay, so this is a case 1. Let me think about, what about if your PA star, PB star is 10? So let's understand this. Actually, this is more important to understand the statement as well. Which one has a higher boiling temperature, boiling point? A or B? What is a boiling point, right? Boiling point A, boiling point B. Which one has higher boiling point? Maybe before asking that, which is more volatile? Which is more volatile? So vapor pressure for A is 10 times bigger than vapor pressure for B, right? So which one likes to escape? A, right? A has a higher tendency to shoot the molecule into the vapor phase, so the vapor pressure is high. So that means which is more volatile? A is more volatile, right? So A likes to be in the gas phase more. So boiling point of A is lower than this boiling point. So it's the same statement. The three statement is the same. Okay. For that case, what you have here is the same drill, XA